Okay, now we're going to look at some examples that you might see on homework number 61. You'll see that we wrote number 5 and number 6. So this kind of question goes with those homework questions, question number 5 and question number 6. Okay, for this example, we have cosecant raised to the power of 10. So the cosecant is going to be our u. And if you remember from the derivative rules, the derivative of cosecant is going to be negative cosecant cotangent. So we need a negative cosecant cotangent right here. Now, we have a cotangent, and we can borrow one of these cosecants. There's 10 of them. So if we borrow one of them, there's only going to be 9 left over. The problem is we're still missing a negative. So we're going to have to put -1 times -1. I can put a negative inside here, and then I'll put a -1 on the outside. And now this part is going to be du dx. It's right next to a dx, so our dx's will cancel, and we'll just be left with a du. So again, the tricky part of this is that originally a lot of people might have thought, well, we're going to have a u to the 10 because our cosecant is our u, so a lot of people would think that we would have u to the 10, but we needed to borrow one of the cosecants in order to get our du dx. So we ended up with actually u to the 9. And so that's what's a little bit tricky about this one. Okay, this is an easy integral to do. We're going to get u to the 10 over 10. We want to put our plus c. We don't want to forget this negative, bring down the negative. And of course, we have to plug in for our u. Our u was cosecant of x. Okay, after replacing the u with cosecant of x, we get our final answer. Let's put it in a box, and that's it. Okay, for the next few examples, we're going to be using some of our basic trig formulas, so that's going to be the tricky part. But once we use those formulas, the integral actually becomes pretty easy. The rule is that sine of 2x is going to equal 2 times sine times cosine. Of course, ours is not x, ours is theta. That doesn't make much of a difference. It's just a different letter. So here our first step is just to use that rule and trade sine of 2 theta for 2 times sine of theta cosine of theta. And that's pretty much it. Then we just organize it. We have cosine of theta times cosine of theta. So that's cosine squared. We can bring this 2 to the outside, so our 2 is now on the outside. And because we have cosine squared, we're going to choose our u to equal cosine of theta. Of course, the derivative is going to be negative sine of theta. So that means we're going to need a negative inside here if we expect this to be du d theta. Can't put a negative in there unless we also put a negative on the outside. Okay, now we have du d theta right next to d theta. So our d thetas are going to cancel, and we're just left with a du. So these two things turn into our du. And now it's an easy integral. It's just a power of u. We're going to get -2, and our integral becomes u to the 3rd over 3. Don't forget your plus c. We're almost done. We just need to trade the u for cosine of theta. And now we're done. Let's put a box around the answer. And that's our final answer in the green box. All right, for this one, we're going to use the rule that the cosine squared of your angle is equal to this stuff here. So we have cosine squared, and our angle is 2x. I want you to notice, because this is very tricky, that your answer is cosine of 2 times your angle. And because our angle is 2x, we're going to have 2 times 2x. That's very tricky. There's like an extra 2 there. If you make a mistake, that's probably where you would make your mistake. After using this rule, the rest of the problem is not too bad. We have a 2 on the bottom, so you can bring it out to the front, and it would become a 1/2 out front. Of course, 2 times 2x becomes 4x. That's the part you got to be really careful about. And I'm going to break this integral into 2 separate integrals. So it's going to be the integral of 1 plus the integral of our cosine. Now this is another spot where we have to be very, very careful because we have a 1/2 outside of that integral, and the 1/2 has to go on both pieces. So be very careful about that. It's 1/2 times our integral, but we're breaking up our integral into 2 pieces. The 1/2 has to go on both pieces. I think most of you can see that this is going to be a very easy integral to do over here. But this integral is going to be tricky. We're going to need a u substitution for that. So if we let 4x equal our u, then du dx is just going to be 4. So that means we're going to need a 4 here. So we're going to have to put a 1/4 out front. Remember, the 4 is your du dx, and it's sitting right next to a dx. So our dx's will cancel, and you're just going to be left with a du. So these two things become the du. Don't forget our 4x was our u, so you can plug that in. But look at our two fractions. Our two fractions are now going to become 1/8. This first integral is really just the integral of 1, so that's how we're getting our x. And the constant of 1/2 is just the number in front of the integral. So that's how we're getting our 1/2 x. Don't forget your plus c. Now for the second integral, we have this 1/8, so we bring our 1/8. What is the integral of cosine? Well, the derivative of sine is cosine, so the integral of cosine is going to give us just sine. So that's why this integral is just going to give us a sine. Don't forget your plus c. And because this integral was a function of u, we're going to put the letter u here. But our original integral was a function of x, so don't forget to trade your u for the 4x. Okay, there we go. Our u is 4x. We're almost done. We do have two constants, this constant plus this constant. Normally you would call this c1, and this one is c2. And we can say that c1 plus c2 is either c3 or just c. So if we want to get real technical, that's how it would look. But remember, a constant plus a constant is just another constant. So let's just put 1 plus c. There we go. That's our final answer. Let's put a box around it, and that's it. Okay, before we move to the next question, I want to see what would happen if we would have just left this as one integral. Let's do that real quick and see what happens. Okay, I'm still going to let my u equal to 4x. So my du dx would still equal 4. So I'm going to need a 4 right here. And so then I'll also put a 1/4 right here in the front. Let's do that. All right, now this is going to be our u. So we're going to plug a u there. This is going to be our du dx. And this is our dx. So we'll be able to cancel the dx's. And we'll just be left with a du. So these two things are going to become du. These two constants will become 1/8. Let's plug that in. Okay, there's our u, there's our du, and there's our 1/8 right here. Okay, now this integral is a function of u, so the integral of 1 is going to be u, and the integral of cosine is still going to be sine. Okay, you notice we bring the 1/8 down. Here's our 1/8. The integral of 1 is going to be u, because this integral was a function of u. The integral of cosine is just going to be sine. We're putting our plus c, and of course this 1/8 can go on every single piece. Okay, we still need to trade our u for 4x, because our u is equal to 4x. Let's do that. And after plugging in the 4x for the u, we end up with 4/8 right here times x. And so that's what we have here. We have 1/2 times x. So we got the same answer there. We're still getting 1/8 sine of 4x here, so that's the same. And 1/8 times a constant, we'll just call it c1, is just going to give us another constant. So it's nice to know that you do get the same answer, even though we did it two different ways. And it'll be up to you. You can do it either way. Okay, number 11 on your homework is going to be similar to this example. That's why the number 11 is there. For this example, we're going to use this rule, sine squared plus cosine squared is 1. And we're going to trade one of our sine squareds for 1 minus cosine squared. So you see we have sine to the third. We're going to break it up into sine times sine squared. And we're going to trade our sine squared for, well, you just need to subtract cosine squared from both sides. On the left side, these two things cancel. So you're just left with sine squared. And on the right side, you get 1 minus cosine squared. So that's why we can trade our sine squared for 1 minus cosine squared. You can see we trade it right here. And because we have cosine to the power of 20, our u is going to be cosine, and the derivative of u is going to be negative sine. So we're going to need a negative sign. We have a sign. Notice we moved it over to here. But we're going to need a negative next to that sign. We're going to combine all these cosines. The way that we do that is we're going to do cosine of x to the power of 20 times each piece. So that'll give us cosine of x to the power of 20 minus cosine of x to the power of 22. Again, our u was cosine. Our du dx was negative sine. We just have a sign. So we're going to need a negative. We'll put a negative 1 here. And we're also going to put a negative 1 on the outside. But now we have a du dx sitting right next to a dx. So the dx's will cancel. And we're just going to be left with a du. So this is a pretty easy integral to do. It's just powers of u. Okay, you might notice that we have a negative on the outside of our integral. So we're just going to leave that on the outside. Our actual integral is going to be u to the 21 over 21. And then minus. And then u to the 23 over 23 plus a constant. I want you to notice that I'm calling it C1, and that's because I still need to multiply negative 1 times each piece. So I'm going to end up with minus C1, which is just going to be plus C. Okay, don't forget we have to plug in the u, and our u was equal to cosine of x. So let's plug that in. And just so it looks nicer, a lot of people prefer to switch this one with this one. Remember, a plus b is equal to b plus a, so you can just switch those two. And that's it. That's our final answer. Let's put a box around it. Now we're done. Okay, questions 12 and 13 on your homework are going to be examples of integrals that are equal to tangent inverse. So let's take a look. We want our integral to look something like this in the end. And again, this number down here can be any number. It doesn't matter. If it was a 25, we would write it as 5 squared. So our a would either be 5 or negative 5. It wouldn't matter. Or if it was a weird number like 7, we can always write it as square root of 7 squared. But that would be a challenge example. That'd be more tricky. So we want this piece right here to equal our u squared. So we can write it as 3x to the third squared. That's the tricky step. So that 3x to the third is going to be our u. And then the derivative would be 9x squared. So that means we're going to need a 9x squared right next to our dx. We have an x squared here. So we're going to put a 9, but then we're going to have to put a 1 over 9 in front of it. And now we have our du dx sitting right next to our dx. And of course, we can cancel the dx's. We'll just be left with our du. So these two pieces on top are going to become just a du. Remember, 3x to the third was our u. So we now have a pretty reasonable integral. We have a special rule for that integral. This is a 1 squared, so we're just going to let our a equal 1. Let's do that integral. So the 1/9 is going to be on the outside. Our actual integral, according to the rule, is going to be tangent inverse. And because our a was 1, we put a 1 on the bottom here and a 1 on the bottom there. We still need to trade our u for 3x to the third. And if we want, we can distribute the 1/9 on both pieces. So this is going to have to be a C1. So you'll notice the 1/9 has been distributed on each piece. And we can trade 1/9 C1 for just a C. And of course, our u was equal to 3x to the third. Let's plug that in. There we go. There's our final answer. Let's put a box around it. And now we're done. Okay, here's our last example. We cannot choose the bottom to be u because the derivative would be 2x minus 6, and that's not sitting on the top. What we could try to do is we could try to complete this square on the bottom so that our final answer is going to be u squared plus a number squared. Let me show you what I'm talking about here. In order to get a perfect square, if you have x squared minus 6x, the rule says that for a perfect square, That would be x minus a times x minus a. You're going to have x squared minus 2ax and then plus a squared. So this is what we have. We have x squared minus 2 times 3 times x. So in this case, our a is going to be 3. So we're trying to get x minus 3 times x minus 3. That's what we're trying to get. So to get a perfect square, we would need a plus 9. So we need a plus 9 to create the perfect square of x minus 3 squared. So we need a plus 9. We have a plus 25. So we can either do plus 9 minus 9, or we can break up the 25 into plus 9 and plus 16. So that means this becomes a perfect square. It's going to be x minus 3 squared. The other piece is 16. We can write 16 as 4 squared because we're trying to match it up with our rule. Our rule has a constant squared plus u squared. Ours is u squared plus a number squared. So we can switch it if we want it to look exactly like the rule. Remember, a plus b is equal to b plus a. So we can just switch this with this, and then it will match up with our rule exactly. We'll have a number squared plus u squared. Of course, we still have dx. We got to change that for du somehow. If our u is x minus 3, then du dx is just going to be a 1. So we can always just multiply by 1. That doesn't do anything. And now our 1 is going to be du dx. That's what it says right here. Du dx is 1. So now we have our du dx sitting right next to our dx. So we can cancel the dx's. We're just left with a du. So these two pieces become our du. And now we can just match up our integral with the rule. Our a is going to equal 4. That's really important. We have 4 squared. That matches up with a squared. So if 4 squared is a squared, we can say that a is 4 or a is negative 4. It wouldn't matter which one you use. You would get the same final answer. Let's go with a equals positive 4. Okay, because our a was 4, we're putting a 4 in this spot right here and also in this spot right here. So there's our a right here and right here. Now the only thing we have left to do is trade our u for x minus 3, and then we'll be done. There we go. Our u has been traded for x minus 3. So this is our final answer. Let's put a box around it. And now we're done. Okay, before we go, I wanted to do a couple of quick examples of completing the square. Normally how I would do it is I would say, well, the number that you need over here is going to be half of this. So half of negative 6, and then you square that number. So that's the number that we need. So half of negative 6 is going to be negative 3. And if you square negative 3, you get 9. So 9 is the number that you need. So if we know that we need a 9 in this position, we can break up the 25 into 9 and 16. We'll bring down the other stuff. And this becomes a perfect square. It's going to be x, and then it's going to be half of negative 6. Half of negative 6 is minus 3. Of course, you can bring down the plus 16. That was the example that we just did. Let's do one more example where it's a positive here. Again, we want to do half of 10, and then we want to square it. Half of 10 is 5. If you square 5, you get 25. So we need a 25 in this spot to make a perfect square. So if we need a 25 here, we can break up the 35 into 25 plus 10. Let's bring this stuff down. And this stuff becomes a perfect square. It's going to be x, and then half of 10. So that's going to be a plus 5. You can bring down the plus 10. So on the left side, we had a minus 3 because this was negative 6. On the right, we're getting plus 5 because this was a plus 10. And if you wanted to write the 10 as a number squared, you could write it as the square root of 10 and then squared. So for an example like we just did on the previous page, we would have to choose an a, and I would let my a equal square root of 10.